And now we're going to talk about a linear correlation coefficient. This linear correlation coefficient is sometimes called small or large r, and it measures the strength of the linear association between two variables using r for determining correlation. The computed value of the linear correlation coefficient r is always between -1 and +1. If r is close to -1 or close to +1, there appears to be a correlation. So notice how straight this line is. If I have a lot of points, I can't tell because they're all in a line. And that line, when I read this from left to right, we can see that it's increasing. It's starting small and getting bigger as it goes. It has a positive correlation. Now, I can still see that this is a line going up. The points are scattered a little more around that line, but I can still tell there's a line. And 0.8, it's still pretty good. Now, notice at 0.4, it's getting harder to tell. We know it's not going down, but you can almost tell it's increasing, but it is getting harder and it's got a very small r. And this one, 0, you can't tell anything. It just looks like it's going around in a circle. And then again, -0.4. If this is going up, this is coming down, but it's not very distinct, which is why it has a small r number. When I talk about r, let's talk about the absolute value of r, or just if it was positive. If it was positive between 1 and 0, and it could be 1 and it could be 0. This means absolute value, and it just means make it positive. Okay, so this means absolute value. And it means, it actually means distance, but it's just always positive. That's a good way to think about it. Okay. So even if my r is negative, it's still, I put the absolute value around and I say, okay, let's make it positive. It's going to be somewhere between 0 and 1. That's basically what that means. So these two numbers, the absolute value of them, are still very small numbers. They're very close to 0. Now, I know this looks like it's a smaller number, but it's not, because we're talking about the absolute value. It's just, the negative just means instead of going up, the line is going down if I read it from left to right. Right, this is going up and this is going down, which gives me a negative value. And then we have this 1 here, which is a very nice line. Imagine that I put this on an XY axis. Let's say this is X and this is Y. We can see that as X increases, Y increases. And that's true everywhere. Here, here. It's not really true here, though. As X increases, Y doesn't change. There really is no correlation because X can do anything and Y just stays the same. So it's really it has no correlation. This would actually be 0. Even though it's a straight line, as one thing changes, the other one does nothing. They can't have anything to do with each other. It's like saying, if I cut my hair, your hair doesn't get shorter. There's no correlation between me cutting my hair and you cutting your hair. We could have a line that's straight, but there's no correlation between them. And then notice as we go to negative, as X increases, X here is increasing, the Y value is decreasing. That's what gives us our -1. And it doesn't matter how much of a slope there is. It only matters that it's going down. As X increases, Y decreases for negative, and as X increases, Y increases for positive. Now we can see that here, there is no linear correlation. There's no lines. These are zeros. They form some nice pictures, but how do we find out something about correlation? If the computed linear correlation coefficient R lies in the left or right tail region beyond the table value for that tail, conclude there is sufficient evidence to support the claim of linear correlation. Let me break that down for you into English. Let's say I talk to 10 people. I have 10 pairs of data. That means I have a critical value for my R of 0.62. This is 0. This is 0.632. And here we have negative 0.632. Because remember, we can go from -1 to +1. And the value that it's giving me here is just the positive. There's always going to be a positive and negative critical value. And my critical values are right here, critical value, and right here, critical value. If my R is between those two critical values, we can see that there is no correlation. That means it could happen randomly. If it's between here and here, it could be a coincidence. It could not be a coincidence, but we don't really have enough data to tell. If it lies outside of the critical values, here and here, this means that we do have a correlation. If the R value is bigger than positive 0.632 or smaller than negative 0.632, then we can say we do have sufficient evidence to support the claim of a linear correlation. If it's in the middle, then we conclude there is not sufficient evidence to support the claim of linear correlation. For a data set of brain volumes, centimeter cubed, and IQ scores of 8 males, so 8, that seems important. The linear correlation coefficient is R equals 0.277, which seems small. Use the table available below to find the critical value of R. There's my table, and I have 8 pairs of data. I have my number line. I have 0.707. Let's make this 0, negative 0.707. We always have the plus and minus. And my R is right around here, 0.277. What did we just say about the critical points? These are my critical values. First, we put in the critical value. We put in 0.707. You can put in plus here, and then you can put a comma and minus, or you can use this little plus minus, which means I want the positive and the negative of that value. Either way, whatever you like best. And that's perfect. All right, since the correlation coefficient R, so we know that's 0.277, and we put it on our graph, is between the critical values, there is not sufficient evidence to support the claim of a linear correlation. Remember, no correlation between the two values. And there we have it. Now we're going to look at a correlation between shoe print lengths and heights. And you can see here that we've taken just 5 data points and we've plotted them. For example, I'm saying that this is my X value and this is my Y value. If I want to plot 29.7, 175.3. It's between 29 and 30. And I would say, and 175, this is that point, 29.7, comma, 175.3. And I could pick another point. Let's pick this point. 31.8, very close to 32. And 175.3, this point right here would be 31.8, comma, 175.3. Remember, whenever I plot an XY, I always plot X first and Y second. This is called an ordered pair. Now, also, if I look here, can I see that there's a linear correlation? Well, it could be. I can say I have a line that goes something like this. And that could be the linear correlation line. And how we tell where the line goes is we look at the vertical distances, the distance from there to there, and the distance from here to here, the distance from here to here, the distance from here to here, and we add those up and we try to find the line that produces the smallest distances between the points. Because I could also pick a line maybe that goes this way or this way. We don't know which way, but what we want to do is we want to find the vertical distances, add them up, and whichever line produces the smaller vertical distances, that would be your line of best fit. And here we're only working with 5 data points, so it is a little more difficult. I'm going to do this for you in StatCrunch. This is going to be shoe print length, and this is height. First point is my X is going to be 29.7. Height is 175.3. I have 29.7 and height is 177.8. 31.4, 180. Okay, that's right. 31.8 and 175.3. And last, 27.6 and 172.7. First, I want to do our plot. So I'm going to go here to graph, scatter plot. And my X value is going to be shoe print length, and my Y value is going to be height. And that's really all I need. I'm going to hit compute. We can see that this looks exactly the same. These points are the points in my graph. For example, if I want to find this point, my X value is 29.7, close to 30, and 175.3. This point right here looks like it's going to be 29.7, comma, 175.3. And notice we have another 29.7, so that must be this one right above it. That point is 29.7, comma, 177.8. 5 points you could actually do by hand. There it is. I have my scatter plot. It looks like maybe it's going up. We could draw a line right through the middle of the two of them, like maybe here. Who knows? Maybe here. We don't have really a lot of data points. It's very hard to draw a line. You don't have really enough data. Next, it's not really very clear whether there is a linear correlation. Here, we can see that my R is 0.591269. So let's say 0.59. Well, it's not that close to 1. It's not really very big. Let's see how we get that from StatCrunch, because part of the point here is to actually get the data. Here's the original, and I want shoe print. So I'm going to get rid of all this and height, right? That's the two things we were looking for. So I am going to copy, and let's see if I can paste it in there. There we go. exactly what I wanted. Now I have the 40 points that were in the original file. And we want to see, does anything change here? Let's do the graph. So I can do a scatter plot. We know shoe print, height. And let's compute. There's my scatter plot. It's still going up. And I can also go here and go into regression, simple linear. And I'm going to pick X is shoe print, Y is height. And that's, I think, all I need. And that's how I get my table that has all the information in it that tells me about my graph. Notice my correlation coefficient has changed quite a bit. It was 0.59, I believe. Now it's 0.81. That's a lot better. This was with 5 points is 0.59. And we don't really know much about it, but we can also look at our P numbers.